So what I wanted to talk about today is point clouds. Typically when we're dealing with 3D objects, we think about our basic meshes. We have a square here, we have a triangle here, and on these triangles we have a face right here. On this box here, we have a square face here. But most of these, all objects really, you see the lines here, those are just illustrations that I made to kind of show the separations. They have 3 points. You have a point here, a point here, and a point here. For your pyramids, your triangles, etc., you have the 3 points. Typically, most software wants you to have 3 points to represent a face. Some will use quads. They don't prefer it because it's more efficient to use triangles. So the square is actually broken down into 2 triangles instead of a singular quad face. So point clouds, what they have is points. I'll go ahead and illustrate the square. So we have 1, 2, 3, 4, 5, 6, 7, 8 points. And they represent, well, not yet actually. You have a face here, a face here, a face here, face there, and a face there. So you have 1, 2, 3, 4, 5, whatever. You have 6 faces. And just kind of like an illustration. I know it's not exact to scale. So those points actually have information in them. They're the X, Y, and Z coordinates. So typically your X is going to be on this side, or it doesn't really matter because like even in this environment, the X and Y and Z's are constantly changing. Well, I'm changing within the X, Y, Z, but you can't exactly tell where that's at. But each computer program has its own system, and for this little demonstration, X, Y, and Z, some software will change these 2 out. So just keep that in mind when you're working with them. So I have an X, Y, Z here, and X, Y, Z here, and an X, Y, Z for that one. Now, I circled this one, not really, it doesn't have to be this one, it doesn't matter, but you have your face here. It doesn't represent one yet, but these set of vertices, 3 vertices, create a face. So this right here, actually the gray here that you can see, or the black, would be the entire face. So it's actually made of 2 triangles. These XYZ coordinates is what makes up the lines which will make up, this would be the face, I guess, if it were actually filled in flat. So point clouds are basically, now you can't really say they're this because they are actually this without everything but the points. A point cloud just consists of the X, Y, Z, and sometimes other information. So a point cloud file, let's go and change the color here. A point cloud file, we'll make this an ASCII file. And then we'll make this file over here a binary file. So for an ASCII file, basically we can actually write in the line of code X, Y, Z, and you can write the number, the coordinates, if you will, for each one. A vector is basically a set of X, Y, Z coordinates. So you could write it in, and each of these is written as like a float, which would be 3, 2, 4, 5, dot 1, 2, 3. you have basically 7 digits here, and that would represent a float. A double is double. What's actually called a double float? A double float would be, and I'm not sure if it's exactly this, but you could take this dot right here, you can move it over to, I believe, here, add a digit, and then have 3 more levels of precision. This is very helpful for when you're using very large point clouds that extend far beyond um, like a very large, I would say beyond 1,000 meters, because, well, actually probably 10,000 meters. You actually want 9. And what this would give you is millimeter precision, because actually 99. So you have 9,999.999. That's obviously not a 9, but let's just pretend. So you could go 9,999.999 millimeters, within the range of the point cloud. If you have to go beyond that, you typically will have to use a double float number for your X, Y, and Z. And what that does is it doubles the file size. And that matters because if you have 3 million points, and I typically work with files that have at least 50 million points, each X, each Y, each Z is a float. So you have a float which is, and I might be mistaken, is going to be let me see here. So we'll have, it might actually be 4 bytes. A byte is basically 0, 0, 0, 0, 0, 0, 0, 0 times 4, or times 4. So you have this, 1, 2, 3. You have these 4 lines that make up a float. So for a double float, like we were talking about earlier, will be double this. There's numbers here as well. Da, 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 da. So let's actually get rid of that. So if you do have 3 million points, you definitely want to have something that is in the float range versus a double float range. For ASCII files especially, because a binary file is actually about 1/8 the size. And it's not always true. There's, variations of this. But since it's written in plain text, it's actually a level above, So you have your characters, which represent, and I showed you a second ago with all the 0, 0, 0, 0, 1s, etc., etc. The machine can process this much faster. If I wrote it down in X, Y, Z, and I have all the characters and all that stuff in there, it's actually represented this, and it has to code it back into regular binary. So binary files are actually much more efficient to deal with. Anyways, let's get back to this. So I have an X, a Y, and a Z. And then in this, you typically have an R, a G, B, or you'll have an X, Y, Z, sometimes an I. Now, I would say typically an I, and then an IRGB. Sometimes it's reversed. These can be swapped out. But you won't have this and then this and then this. The whole file will have either this type or some other variation of data. It has the XYZ coordinates and information to depict the colors. Some files do allow you to mesh inside of them. Sometimes they're proprietary. I've only seen one time, and I'm not really sure if it was proprietary, who owned it, etc., etc. I typically only work with the ASCII file type and sometimes the binary file type. And for an example, so an ASCII file type that's pretty common is a PTS file, a ply file, as I call them, or an XYZ. And it's very interesting because this would actually make sense to use the most, XYZ file for XYZ coordinates. I believe that these two can actually be ASCII or binary. And when you're opening them in the program, it'll oftentimes either figure it out itself or it will ask. This one is your standard ASCII. There is another type. I don't remember. It actually might be both of them. Let me get back here. So you have a LAS file and a LAS file. One of these actually has some pretty serious compression. So you can get down, and I've done it before. I've gotten down like a 40 gigabyte file down to, I think it was like 12 or something along those lines. I've messed with different compressions. File size is a big deal because when you're working with several projects, I mean, 40 times 10, you have 400. In a year, you'll use up your 1 terabyte space. So we have kind of all this explained as far as we have the points, we have the 2 file types that you would use. You have several lines of code. Sometimes they actually have like X, comma, Y, comma, Z, comma, I. And this represents the separator. But if you really think about this, you have code for that, code for that, code for that, etc., etc., etc. So sometimes it's kind of a pain to work with these. So they'll typically actually put a space. Regardless, the space uses data as well. That's why binary makes the most sense, and it just writes X, Y, Z as binary. So whatever number this would be, and then it knows that that it has this many bits data, and then it knows that the next one will be the next set of data. So it doesn't have wasted space. It just has, and this isn't actually there. It's just the 0, then the next 0, but it knows that that's there. So binary is the way to go. If you don't work with a standard, which like the LAS and the LAS are kind of like they're pretty much the go-to standard for storage because they're very standardized. They're a little bit difficult sometimes because you can actually put a lot of metadata into like this file right here and just encode it. I'm pretty sure it's I want to say LAS, but so yeah. So point clouds are just representations of vectors. You have a XYZ here, XYZ here, XYZ here. They are represented by float. And I might have to edit this and come back because I can't really think of what else I wanted to say. I think that's really it. All right. Thank you.